Now we're going to shift gears. Okay, I know it's only been 2 days, but we're moving away from logic and we're going to shift towards sets. And the reason I'm doing sets right away now is because sets build on logic. And the things that we're going to prove about sets and the connections to computer science, we can prove using the very things that you just learned about logic. By the way, if you look at other books, the order of how discrete math books are laid out is completely varied depending on the book. And this guy really has thought a lot. And most of the way he's ordered it is the way that I would order it too. The way he does logic and then sets, that's very unusual. Most people don't do it that way. A mathematician always starts with sets and then does other stuff. And in computer science, it makes more sense to do logic first. And I'll show you why. Let's start with sets. Where do sets come up in computer science? When you're writing a program, say somebody's typing stuff in, and you want to check if the last thing they typed is a vowel. So you'd say, hey, is the last thing this person typed in this set, A-E-I-O-U? Right? It comes up in your programs. It comes up in data structures. The easiest way to represent a set in Scheme is to just have a list. But you should realize that in mathematics, a set has no implicit order, even though in Scheme there would be an implicit order. So a set is just a collection of things. And you can write a set just like that, A-E-I-O-U. What a nice clean blackboard. Or you can describe a set in words. Here's the set of all even integers. All x such that x is an even integer. You can write sets like that. You can describe them in English. You can list them. Sometimes you'll even see strange things like this. It's not very formal, but everybody knows what this means. It's a set of all natural numbers.
In that first one, how do you know there's all x even though you don't have the for all symbol?
It's just the notation. When you use sets, you give a variable. This means such that, and then you give the condition. So it's implicit that it means for all. There's a lot of different language to learn in doing math, but it's all pretty logical. You describe a set. There's a particular algorithm that I mentioned last time that came up when we talked about trees, called the minimum spanning tree. This has come up twice, so I'm actually going to talk about it for just 2 seconds. Here's a graph with some weights on the edges. And the minimum spanning tree of this graph is a tree that hits all the vertices that has the smallest weight. So one horrible way to do this, as I mentioned last time, is to try all the trees and see which one has the least weight. That's terrible. But a faster way, and there's a lot of ways to do this, is you start with the smallest edge, and you include that. And then you connect the next smallest edge, and you include that. And then the next smallest. And as soon as you've connected all the vertices, you're done. And this is actually the smallest weight spanning tree of this graph. Okay? And this algorithm was known maybe about 30 years ago by now, invented by a guy named Kruskal. There's another version by a guy named Prim. The point of it is, when you actually implement this algorithm, one of the fastest ways to implement it, one of the fastest ways to make it run, is to have a data structure that uses a set. And the set is a collection of these little piecemeal trees before they get connected. And you build the sets into bigger sets until you have just one big set. That's the final spanning tree. And that data structure is sometimes called the union-find data structure. You've got to be able to combine sets into bigger sets. And you've got to be able, given a vertex, to find what set is it in. So as you're building it up, you might have different vertices and different pieces of different trees. If somebody says, what tree is that vertex in? What piece is it in? You want to be able to find that out. I'm not going to do any details about this, but you should know that it's one of the fundamental algorithms, and it's used as a big, big important data structure. All right, so sets come up a lot. We're going to do some of the basics of sets. Here's how you describe sets. Here are some of the operations you can do on sets. Let's prove some of these operations. Let's make sure we know how we can manipulate sets. And for that purpose, here's how it works. Whenever you talk about sets, there's always a set called the empty set. It's a set of nothing. There's nothing in that set. There's also something called the universal set. Whenever you talk about a set of things, presumably they're all subsets of some bigger universal set. So your universe might correspond to, say, all the numbers in the world, and then this would be a subset of that universal set. This would be a subset of that universal set. This would be out of the universe. All right, so whenever you talk about sets, you have a universe you're talking about and then subsets of that. And because of that, you probably learned this in grade school. You have this picture where a big rectangle represents the universe, and your sets are these circles. And sometimes sets overlap. They intersect. They have things in common. And these diagrams are called Venn diagrams. And they give you a picture view of what's going on with these sets. So we're going to get back to these later, because we're going to do some counting with these that will actually help us solve some pretty cool problems.
What would be outside of the universal set?
That's like what's outside of our universe.
Well, didn't you pointed to something over there instead of
In this example, I said these two, say this is the even integers, and these would be, say, the natural numbers. So this might be all possible real numbers. It's just a big, big, big collection of things that all the sets we're dealing with are subsets of.
So if the universe is all real numbers, then the vowels are outside because they're not.
Right, because there's no vowel. Right. The vowels aren't part of our universe. And you can make the universe just be everything in the whole world, and in which case everything is there.
Well, E is.
Yes. Yeah. And I guess, yes. Troublemaker. A union B equals B union A. It's so transparent that if I asked you to prove it, you'd all give me a groan and go, well, I know it's true, but what do you mean prove it? Here's what I mean by prove it. What does A union B mean? What does it mean to be an element of A union B? What does it mean to be an element of B union A? If I want you to prove to me that these two sets are the same, you'd have to prove to me, look, it's a long-winded proof, even though it's trivial and transparent, but here's what you'd have to do. You'd have to say that if X is an element of A union B, then X is an element of B union A. That's what you'd have to prove to me, and then you'd have to prove vice versa. That if X is an element of B union A, then it's an element of A union B. You have to prove those two things to show that these two were identical.
Is that a general way to prove equivalency?
Absolutely. Show that the implication goes both ways. In fact, equal in sets is the same as double implies in logic. How do you do this? Just unravel it into logic. X, an element of A union B, implies X, an element of B union A. How do we do this? We want to show that this is true. What does X, an element of A union B mean? It means X is an element of A or X is an element of B. And what does this mean? X is an element of B or X is an element of A. Well, I can turn these two around. How come? Because OR has the commutative law. I can turn this around because I know I've already proved the commutative law for OR. So whatever works for OR is going to end up working for union. You just unravel it. Or XA. And at this point, I can stop and I can say, hey, you know what? It goes both ways. These two are identical. It's definitely true. This direction and that direction, these are identical. This proof is trivial. There's nothing to do here except unravel it, reverse the OR because you can do it for ORs, and then see that you get two identical things. It's a little less trivial for an example I'll do in just a minute. I'll do the distributive law for sets, and we'll run through it the same way. Unraveling the definition into logic, using the rules we know for logic, seeing that it works, and being done. I'm going to do just a couple of these because they're really dry, and I want to go on to interesting stuff. Yeah.
Make the step at the third and fourth line there.
Here to here?
Yeah.
This is a definition of A union B. X is an element of A union B if and only if X is an element of A or X is an element of B. That's definition. Okay, so if you gave a reason to go from here to here, it would be the definition of A union B, the definition of union.
And so,
Yeah, Chris?
the implication from something to itself is we're done. That's
You could make a truth table for this, right? You just make a truth table for any possibilities of A and B. Here it's identical to this. So actually,
as far as deciding when we're done with a proof, though, if we get an implication from something that's identical on both sides, we can call it good.
that's like C implies C.
Right. Sounds good to me, but
Well, no, just make a truth table.
Would you accept as a proof that we just make a truth table on each side?
Sure, you could do that. If you take all the possible values for C, 0 and 1, and you check C implies C, 0 implies 0 is true, 1 implies 1 is true, so this is a true formula, C implies C. Actually, this is a true formula too. You wouldn't even have to go through and do it backwards. You're already here. Okay? Other questions? Let's do an example that's a little more involved than this trivial one.
Shai, you'd also have to show that vice versa, right? You just showed that for 1/2.
Right, but actually, at the bottom there, we had already done it vice versa, because we had an identical thing on the left and an identical thing on the right. You'd have to do it, but it would be the exact same thing.
Right.
And you'd get the exact same result, and you'd, right, yes. Yes is the answer. Okay, let's do a, let me give you the distributive laws. It's just what you would expect, that union and intersection distribute just like and or. There's one distributive law. Who wants to give me the next one? Not you. A and B or C, good, equals. A intersect B union C equals. A intersect B union. Stop saying and or. It's the same thing as what we did before for and or. It works for union and intersection. It's the exact same idea. And the proofs behind these are going to be the same proofs that work for and or. We're just going to unravel the definitions, turn them into ands and ors, and see that the theorems are true. And we're going to pick one of these and do it. And I'll leave De Morgan's laws for you to prove in the problem set. So I'll write down De Morgan's laws here. You want the complement of A union B? 1 second, Donna. Look. What's your question?
I just don't know when you're using union, intersection, and or.
These are all unions and intersections. Yeah, so you know what? I will, I'll try to make them sharper, the ands and the ors, so you'll see. But these are all unions and intersections.
Okay.
Here's De Morgan's laws, that the complement of A union B is the complement of A intersect the complement of B. Let me make sure everybody knows what this means by a picture. Here's A, here's B. A union B is this. Okay? What's the complement of A union B? It's all this stuff. All right? That's the complement of A union B. Is that the same as the complement of A intersected with the complement of B? Let's think about that. The complement of A is everything except this hole. The complement of B is everything except that hole. Where those two things intersect is every single place except this funny binocular shape. You can go through this with pictures and convince yourself that it's true. But we're going to prove it, or you're going to prove it on your P set by unraveling the logic. You can always do it with pictures to convince yourself, and you can always check it with logic formally. We're going to do one of these now with logic. Now let me stop for a second. Are there questions so far? Yeah, Sharon.
Is that saying that complement, the union of the complement of AB is the same as the intersection of the complement of AB?
This says that if you take the union of A and B, and then you complement it, that's the same as if you complemented A, complemented B, and saw what was in common between them. Okay? So that's this picture. Let me do this picture. Here's A. I complement it.
Dot in the B for us.
I will. There's B. I'm going to complement the B by going the other way.
Go through these.
Yeah, you gotta go through the.
And where they both share places is every place outside of that binocular spot. That's where I get cross hatches. So that picture is the same as that picture. Does that make sense? Okay. Questions? Other questions? Let's do one formal proof of this so you'll see how to do it. And then let's move on to something that's more fun. I promise, Donna. All right, we're going to prove this particular distributive law for sets, that they distribute through this way. This is the only proof like this we're going to do because they're boring. And because once you know how to do them, you get the idea there's other more fun stuff to do. So let's do it. We're going to show that this is equal to this, that they're equivalent. Rather than do a double implication, like we said we would do before, we're just going to take this, unravel it. We're going to take this, unravel it, and we're going to show that we get identical things at the bottom. Okay? So we'll kind of do it simultaneously.
Do you need to unravel it? Isn't there some theorem that you can just replace intersections and unions?
Well, this is a theorem, but we have to prove that it's true. No, you could probably prove a general theorem that if you replace any union with an or and any and with an intersection, that the corresponding theorems from Boolean algebra remain true. You probably could do that, but we're going to do
I
this.
just wonder what the relationship is between the set theory and the logic. Are they just the same? Or
No, there's differences. Set's more general than logic for many things. Logic's more particular and gives you applications in circuits and various other things, and sets is more of a mathematician's way of defining bigger objects and a data structure in computer science. What does this mean? That something is an element of A union B intersects C. What does it mean to say that something is an element of A union B intersects C? What does that mean? Unravel that in logic. Joe.
It means X is an element of A,
Good.
and X is an element of B intersects C.
And? No. Or. Or X is an element of
the intersection of B and C.
Good. Can we unravel that a little more?
X is an element of A.
X is an element of A, or
Parenthesis. X is an element of B and X is an element of C.
good. Okay, this is what I have so far. Let's do a similar thing on the other side. Well, let's do a similar thing on the other side. X is an element of A union B intersect A union C. Let's unravel this. Heather, I promised I'd call on you today. Can you help me?
X is an element of A, B, C, X is an element of A,
You believe me, huh? Perfect. Perfect. Heather's right. X is an element of the first one, and X is an element of the second one. How do we unravel this? Doug, you want to unravel this thing for me? What does it mean for X to be an element of A union B?
X is an element of A, or X is an element of B, close parentheses, and X is an element of A. We need parentheses around this, by the way, or X is an element of C.
Excellent. All right. Who sees what's going to happen here? There's one more step.
Distribute out of
Let's distribute this side out using or distributed over this and. We get X is an element of A, or X is an element of B, and X is an element of A, or X is an element of C. And Why?
Wow.
Wow, right. These two are identical. We're done. All right, this is as dry as this course gets. I'm not going to do any more. You'll do a couple yourself. Make sure you know how to do it. You should understand that proofs about equalities and sets are really based on the logic that you learned. And now let's do some more stuff about sets. All right, let me stop for questions about this before I let this go. So Anthony asked before, whoa, we just did the stuff by induction and we kind of plowed into it and boom, we're supposed to do proofs by induction. And yeah, to some extent that's true, but what you're going to be seeing is little bits and pieces and examples of proofs by induction, so that when I really get to the, hey, today we talk about proofs by induction, and you'll see it from the beginning, you've already had kind of an intuitive exposure. So this is going to happen again right now. I'm going to do another proof about sets. It's the last proof I'll do before I talk about counting in sets. And the proof I'm going to do is an extension of this proof. But it won't involve any logic unraveling. It'll be a proof by induction. Here we go. Here's the theorem that I want to prove. One of the things when you do discrete math is you'll find out all these symbols and all this language. And as I told you before, notation makes a big difference. And I like to stick with these ... dots until they get so obscure we have to wrap them up into another symbol. And you'll see an example of this today or tomorrow where the notation makes a difference. But if I can get my notion across with ... dots, then I will. This means if I'm going to take A and union it with a whole collection of other sets that are intersected with one another, I'm just generalizing the last theorem. Instead of one set here, I got n sets. Okay? This is like a dull grad student. Okay? Here's a problem. Here's something to work on, generalize it, and that's the best I could think of. It's just a boring generalization, but it's true, and we should know that it's true. You can distribute over lots of things, not just one thing. Why is this screaming for mathematical induction? Because this is just n cases, and before we did the case where you had 2, right? So it's screaming for mathematical induction. There must be a nice way of just going from one stage to the next, make it nice and clear, and be done with this, and get on to something else. So that's what we're going to do. We're going to prove this by induction.
That's a notational point.
Yes?
You should have 3 dots.
Yeah.
4 dots has a different meaning.
Okay.
4 dots means what?
It means we're extending it out to infinity. You wouldn't use it with an finite.
What's 2 dots?
I don't think.
You know, 2 dots has meaning in some programming languages, depending on how old you are. Well, right, it's a parent, right. It also, it indicates a range in some older, 1 ... n means this is the data structure consisting of all the values between 1 and n when you're talking about ordered. It comes up a lot. Any symbol you can think of has a meaning in some context. There is actually a common gesture in Israel which can mean anything from, you are really bugging me, wait a second, to, excuse me a moment, I'll be with you soon. And it's really hard to know what this is. And all those gestures are bundled into one single body movement, which is something that looks more or less like this. Now, this is so ubiquitous and occurs everywhere in society so often during the day and is so offensive to most Westerners because this, it's typical. You go into some place, you ask for service, and the person's on the phone. The person is supposed to serve you. So, in this country, that's a no-no. You get off the phone, you serve the person who comes in. And you'll sit there and you'll wait 10 minutes, and then you'll finally say, excuse me, and the person with the phone on their shoulder will look at you like this. And, so look, what does it mean? Culturally, it is not a rude thing to do at all. It's completely part of the culture. It's what you do when you simply want somebody to wait a moment, and you'll be with them. So my son, who went to school there for the year. I was picking him up after school, and then he's waiting by the bus stop, and I'm yelling at him, come on, we're late, come on, let's get out of here. And he's playing with his friends, and he runs over to me in the car, and he goes, and I'm thinking, oh no. But anyway, it's a lesson about culture. It's completely an inoffensive gesture, and you have to get used to it, and you have to learn to interpret the time that it's meant to be offensive to the time that it isn't. What does it have to do with this? Nothing, but now I got your brains clear and ready to think again. So the base case is when n equals 2, and we just did that before. We just did that. Okay, that's done. So now we're going to assume that this theorem is true for any number of b's up to n, and we just want to show that it's true if we add one more. Everybody with me so far? How do we do that? We're going to assume it's true here. That's our inductive assumption. We want to be able to get from there to the next case where we add one more b, where we make it bn plus 1. All right, well, let's work with the bn plus 1. That's what we want to prove. And in working with it, whenever we need this assumption, we'll say, I got it. And I'll say, by the assumption. So I don't like to say start with this and work our way up. I like to start with what we're trying to prove, and then whenever we need the assumption, reference the assumption. All right, so here's what I want to prove. I want to prove that A intersect, there's going to be a lot of drawing here. A intersect B1, B2, up to Bn plus 1 equals A union B1, intersect A union B2, dot, 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 A union Bn plus 1. That's what I'd like to prove.
You might put a question mark over the equals sign?
Yes, I certainly will. No, we haven't proved it. We have to prove this now. Right. Is this true or not? How are we going to prove this is true? Do we have anything that's going to help us? We've got a lot that's going to help us here. The one thing we have that lets us distribute through here with sets is what? We have one rule that we already proved that lets us distribute with sets. What is it?
You can expand it out to...
You can expand it out if it has two things in it, right? So instead of having this Bn plus 1,
Bn, and then...
let's turn it into two pieces. This is the same as A intersect B1, intersect B2, intersect B3, intersect Bn, intersect Bn plus 1. Now, what justifies that step? That this is the same as this. What justifies that step? We know that intersection is associative. Do we really know that? I didn't prove it today, but you could prove it. And it's based on the fact that ands are associative. This is because you can do things associatively. And that's the justification. And you should write that down, because intersection is associative. That's how I go from here to here. But the motivation for doing this, the reason why I did this, is because I am dying to get this parentheses into two pieces, not n plus 1 pieces. Because I can work with it if it has two pieces. Here's piece 1, here's piece 2. By the base case, by what I did before, what does this equal? And these really are equals, right? These are for sure. This is because of the associative property. This is because of the base case.
Why are we using n plus 1 instead of n?
We want to show that it's true for n plus 1.
We're assuming it's true for n.
We'll assume it's true for n, but we want to show that it's true for n plus 1. You don't buy that. What's bugging you about that, Doug?
Well, it seems like we were trying to prove that it was for n in the first case, and we just changed what we were proving for here and that.
In order to show that it's true for any n in the whole world, we're going to pick an n plus 1 and show that if it were true for this n, then it'll be true for n plus 1. And that will show that it's true for any n in the whole world.
If we have a base case.
If we have a base case, right. So I picked this n plus 1. I'm going to show that it's true for this n plus 1. And in doing so, I'm going to use in the middle of my proof somewhere the assumption that it really does work for the one before it. You know what? Maybe it'd be easier for you not to feel funny about it if I call this n and I call that n minus 1. Then I'm proving the general case for n and I'm assuming the n minus 1 case. I think it's just a question of which one I called n. but they're both as general as the other. It's just that I need to assume the one before it is going to apply the one that's next. What does this equal based on the base case? Hey, Donna, can you do that? What do I get if I distribute this out?
A union B, 1 intersection A union. Oh.
Keep going.
Oh, you're just distributing it to that one piece.
I only got 2 pieces here. That's the only thing I'm allowed to do.
Oh, all right.
B1, B2.
Union.
Good.
Okay. And then intersection.
Intersected with A union. Good. See that mess? The big ugly mess? Compare this to what we're trying to get on the right side. Are we close now? We're very close. We're almost there. This part matches this part. Check. Check. If we can get the rest of this to match the rest of the part before, then we're done. How do we get that to happen? That's what we can assume by induction. We can assume by induction that A intersect B1 up to Bn is equal to A union B1 intersect A union B2 all the way intersect A union Bn. So I can take this and in its place I'll be able to put in that. I'm not going to finish writing this proof out because it's boring me to death. You finish writing this out. Say last step by induction this piece equals that which is identical to this. Write it out in English. Make sure you understand that part. Who thinks?
I
Yeah.
just don't understand how we proved anything by assuming something and then substituting in our assumption. Can you tell me what step I'm not understanding?
I think the key is the base case, because if you start with 2, then it's true for 3. Then
We know that it's true for 2, and this argument shows how to go from 2 to 3, and we can use the argument again to show how to go from 3 to 4. So Sharon, this shows us that if we're trying to prove that it's true for 3, say n plus 1 is 3. If we want to show that it's true for 3, I've just done it as long as you grant me that it was true for 2. That's what I've done in this argument. I've shown you that I can prove that this formula is true for this number being 3, as long as you grant me the fact that it's true for when n is 2. But we know it's true for n equals 2, so this argument runs through, and now I know it's true for B1, B2, B3. But if I know it's true for B1, B2, B3, I can go through this argument again, and this time I'll make this 4. And since I know it's true for B3, when I get to this point, I'll have that it's true for B4 also. This is an argument that shows me how to get from one step to the next step. Right? A little better? Maybe not. Almost.
I just need to sit down with it.
Okay, that's the whole idea of induction, is that you concentrate on the step. I want to point out, what if I said unravel this logically? It'd be a much uglier proof. Right? You'd have dot, dot, dots through all your proof. You'd have to go through the same kind of dot, dot, dot in the ands and ors. And maybe we didn't even prove it for ands and ors. I mean, it's a little neater to do this by induction. This is a screaming for induction kind of proof. I should say that some proofs are not screaming by induction. Did Tara do this? Did she show you the sum of the first n squares? She didn't show you that. All right. She did show you that? She gave you a formula for this?
N times n plus 1 times 2n plus 1 over 6.
You can prove this is true by induction, but it's the most unnatural way to prove this formula. You know what this formula equals? Here's what it equals. Now, we did this formula in class. This one was pretty logical, right? I gave you a geometric way to look at it. I gave you a counting way to look at it. I gave you a bowling pin way to look at it. Later today, I'm going to give you another way to look at this formula. You can figure out this formula by thinking about it. How many people, if I give you 10 minutes and ask you how to add up the first n squares, are going to come up with this twisted formula? If you really know about combinatorics, you might guess it. But you're not going to guess it if you're just a regular old Joe off the street. It's just not obvious. You could prove this by induction and still have no idea why it's true. I could prove to you that if this is true, I could get to the next step, and the next step remains true. It would be a little algebra. Add n plus 1 squared to this side, add it to this side, rearrange the terms, see if you get n plus 1 times n plus 2 times 2 parentheses n plus 1 plus 1. It's just an ugly, boring, it's the worst inductive proof I can think of. It's just it just ruins the whole idea. What if I said, here's the sums of the numbers from 1 to n squared, and I said, come up with that formula? If you could prove things by induction, you'd still be dead, because you wouldn't know what the formula is. You could do lots of examples and maybe guess at the formula. Maybe you might have a way of guessing at it. There's lots of good ways to guess at it, but you might be dead in the water. So there's another way to prove this, the way that most people proved it back in 1300 when induction was a new idea. They would prove things like this inductively. They would prove things like this inductively, but they would do things like this the way they discovered the formula. They would show you the actual constructive way where this formula came from. And I'll do that, maybe later today, maybe tomorrow. But I'll show you a much better proof that really strips away the magic behind this formula. Saying all that, it's still kind of cool that if you know how to prove things by induction, and you happen to guess this right, that you can prove it's true even though you don't know what's going on. That's powerful. That's a really powerful idea. There's going to be a time when we talk about that 7 rings problem, we're going to try to calculate how many moves does it take to solve that problem. We're going to come up with a recursive formula. We're going to do some tables. We're not going to be able to guess any formula, but we're going to notice that there's a really simple relationship between one number and the next number in the table. That like it doubles and gets added by 1. And we're going to use that relationship, prove it by induction, figure out the formula in a backhanded way, all because we know how to prove things by induction. So it can go the other direction too. Sometimes noticing things step by step is the way to go. Sometimes seeing the big picture is the way to go. And don't ask me how do you know which one is best, because that's what makes mathematicians feel they're special. Okay, if you're good, then you have the right intuition, and it takes years and years to get the right intuition. Yeah, Joe?
If you can assume that you could use the associative property to separate the b to the n minus 1, why do you even have to go to that step? Why can't you just use the associative property on your assumption and prove it out that way?
What do you mean?
All right.
You mean I could go up to b1 to the bn minus 1 here?
No. If you come down to where you're there.
Here?
Where you had the b to the n plus 1.
Yeah.
Then you use the associative property.
To do this, yeah.
Right. Well, if you can assume that you know the associative property and the associative property is true, why don't you just do it with your assertion and show, with your whatever it is you're assuming that a to
I'm assuming this.
Right. Why do you have to go down the b to the n plus 1 if you could just use the associative property on what you're assuming to prove that it's true?
I can't use it to prove that it's true. The only thing I can do with the associative property is parenthesize sets of intersections in any way I want.
Right.
As long as they stay in order.
Right.
And that's what I did here. I could parenthesize these to my heart's content until the cows came home, and I wouldn't be any closer to getting this proof. I could do this up to bn minus 1, and it doesn't do me any good.
See, I don't understand why you had to go prove for the n plus 1 step if you could just prove what you're assuming.
You can't prove it. You can't. There's no assumption that says that A union B1, B2, B3, that you can distribute it out over all the pieces.
No, but you could assume based on the base case that you could do it over 2.
Right. You can do it over 2 pieces.
So if you break that first b to the n to the 1, intersect
into these 2 pieces, this and this.
Right.
Then this equals A union this.
And A union intersect.
Intersect A union that.
Right.
And then you'd have to break this and do this again, and do it again, and do it again.
Right.
That's kind of doing induction backwards. You're starting with your case, and you wound it all the way down to the base case. And this is just going forwards. It's the same idea. You have the right idea. That's the right idea, except that here I just went forward from n to n plus 1, and you're thinking of taking n and working your way back until you get to the base case. But you'd still have to do all those steps. The key thing is showing the connection between the nth step and the step before it, or previous steps before it. Still not, I can maybe address this later, maybe, if it's more helpful. Okay, so now we can put that away, because I don't like these proofs. They're boring. Okay, I want to talk about counting a little bit, and counting that has to do with sets. And this, for me, this is a little more interesting, and at least gets us to a different part of where sets come up in computer science. And has to do with counting. Oh, and here's a great example where the book leaves this for a chapter 4 chapters down that's in the counting chapter, even though it's something that has to do with sets. And I just think that's a bad idea. I think they should do it here. The most interesting thing about sets as far as discrete math goes is something called the inclusion-exclusion theorem. This theorem is so naturally inductive and so logical for the base case and has so much to do with counting that I think you should see it here before you forget all about sets. Because it's the neatest thing about sets that relates to combinatorics. Here's what the theorem says in the simplest version. It says, let's say you have two sets, A and B. And you want to know how many different elements are combined in A and B together, in A union B. Here's how we would write that. When you put vertical lines around a set, that means how many elements are in that set. That's sometimes called the cardinality of the set. So if you want to know how many elements there are in A union B, you tell me. Let's be a little more interactive. And I want a wrong answer here. I'm going to write a wrong answer.
Cardinality, cardinality.
Right? Why is that wrong? Because they overlap, right? If they didn't overlap, that would be right. Right? But they overlap, so that's not right. Right, this is a key, such a key idea in counting. One of the key tricks in counting, remember this, I would say in counting, there's some ABCs you have to learn, and then there's two big tricks. And these tricks can be so subtle and twisted out of shape in so many ways you won't even recognize them as the same trick, but they are the same trick. Two tricks in counting. Trick number one, if you're trying to count something and you can't count it, count the stuff you're not interested in. That's one trick in counting. I asked you guys to read that birthday paper that I wrote. Remember, you're trying to calculate how many different birthdays where everybody's got different birthdays? That's hard, right? But if you count the stuff you're not interested in, hey, how many birthdays everybody's got the same? That is something you can count. It's easier to count sometimes the complement of what you're trying to count. So if you're having a hard time counting something, count the complement. That's one trick. Trick number two, count double or multiple times in a controlled way. That's the second kind of trick that you'll see. I would say that almost every trick in combinatorics can be based on the ABCs that I'll teach you, permutations, combinations, and combinations of these two tricks. This trick is the one we're going to talk about right now, number two. And I'm going to give you a simple example of it, and then I'm going to go back to this example. Remember the triangle numbers, 1 plus 2 plus 3 plus 4 up to n? We figured out a million ways of proving that formula. One is I counted it out. You know, Mike goes with everybody else. And then Chris goes with everybody else except Mike. You know, so that's n, n plus 1, n minus 1, n minus 2, etc., down to 1. We did it another way where we geometrically shifted the things around. Here's another way to do it. Every single person in the class can go with every other single person in the class except themselves. Right? So if there's 36 people in this class, every one of you can be matched with how many other people? 35 other people. That's fine. But that means I counted Doug going with Anthony and Anthony going with Doug twice. Right? In fact, every single pair in that list of combining each one of you with each of the other ones was counted exactly twice. Once from person A's point of view, once from person B's point of view. So all I have to do is take that n times n plus 1, since I counted each value twice from what I really care about, and divide by 2. Now I'm back to what I want. Everybody see what I mean by count double in a controlled way? If I know that I'm counting in a particular way that doubles everything I really want to count, then I can count that way as long as I divide by 2 when I'm done. I think in this example you can really see it in a simple way. And you'll see the same simple idea here in inclusion-exclusion. And this idea you'll see in so many more complicated ways that make sure you get it here. because it'll make sense here if you give it a little time, and it won't make sense in the complicated ways unless you get the basic way down first. Donna.
The example you just gave, where it has to say n times n minus 1.
It would be right to say n times n minus 1. What a polite woman, huh? I once had a student who said, I was writing some C program up on the board like 15 years ago, and I put a bracket in the wrong place. And this guy was a bit of a jerk, and he raised his hand and he go, is that a formal parameter or do you mean an actual parameter there? And I didn't know what he was talking about because I didn't notice this bracket, and I just sat there and going, I don't know, I'm not sure what you mean. And we went back and forth like this for 10 minutes, just killing the class. And finally, I go, what are you getting? And he goes, because I've just never seen a formal parameter really written at that particular spot in the program. And after a long time, he finally said, did you mean to put the bracket there? And I just look at him and I go, oh, God. Give me a break. But Dawn is like the opposite. She goes, excuse me, but did you just make a complete error there and write plus instead of minus? Donna, you're right. It's n times n minus 1 divided by 2. You're right. I made a mistake. Thank you. Thank you. It's the sum of the first n minus 1, right. Because when Michael starts, he can connect with n minus 1 people. And then when Chris goes next, he can connect with n minus 2 people that are left. And we go all the way down to 1, so it only goes up to n minus 1 if you have a class of n. Okay? Let's go back here. We said this is wrong, and Anthony already yelled out the answer before, and he was right, that the reason it's wrong is because we have counted what double? Right. Look at that nice control. Boom, boom. I'm dominating this guy. I know just what we counted double. It's not some weird thing we counted double. We counted this area double. This stuff got counted once. This stuff got counted once. That stuff got counted double. So how do we fix it? Subtract it out, and then you'll only count it once. This is the inclusion-exclusion theorem in the case of 2 sets. Now I have to tell you that there's an inclusion-exclusion theorem in the case of 3 sets, and 4 sets, and 5 sets, and any number of sets. And when you get past 3, there's no drawing it on the board. For 3, I can still draw it on the board. And the way you prove this, and I'm not going to prove it because it's a hairy notation, but how do you prove this kind of thing? It's screaming. Induction, right? I mean, you prove it very similar to what I did before. You use the base case to start out. You take n sets, you associate them, so you get 2 pieces, A1 to AN, and then the n plus 1th set. And then you use your base case to get this, and then it's much uglier than what I did before, but you can do it. I'm not going to do it. The book does it. You can look it up. You can see it. I'm not going to ask you to do it, but it can be done. And it's a classic proof by induction. But what is the theorem? We haven't even said what the theorem is, much less prove it. So let's talk about the theorem. Let's do a couple applications of it. Joe's looking at his watch, but we started really late today. Late. I'll buy you lunch. Let's see. I still got that dollar change you brought me yesterday. That's it. Succotash for everybody. All right. No more counting double. Now we got 3 sets. We're moving up. How do you figure out how many things are in the collection of the union of 3 sets? Let's start again with the same wrong idea. This is not a joke. A lot of times in math, you start with a wrong idea because you got a better chance fixing something that's close than you do sitting there waiting for the light to go off in your head. And I'm completely serious. Don't sit there waiting for the light to go off in your head unless you see it somewhere in the distance, like down the subway line. If you see something coming, you see you have an idea, you just got to work it out fine. But don't sit there thinking, I have no idea how to do this. Do something wrong and fix it. And that's not a joke. That really works. You can often make progress by doing something wrong and then figuring out what's wrong in it. So, you know this is wrong. You know that's wrong because they overlap. So how do we fix it? This is counted how many times? Twice. This is counted twice. This is counted twice. All those things are counted twice, right? Not exactly, right? What about that little teeny piece inside? This is counted twice, this little piece here. this crescent, this is counted twice. This is counted twice. How many times? Lots of times. Oh, it gets really hairy. Well, here's a perfect opportunity to give you a sense of how a mathematician would think. There's two ways here. Do we just go ahead and start subtracting these off and see how far off we are then and continue like we did last time? Or do we try to figure out how many times was this counted? Is it 2 or 6, right? Everybody, 3 or 6. Everybody's got a different idea. There's two different directions. Which way do you go? Right? Well, I'm not going to tell you because nobody's going to tell you in real life when you're working on a math problem. And I'll tell you the truth, either way would be okay. The way that I think is going to get us to the answer faster is to do what we did before, is to notice that these little crescents were counted twice, and let's take them off. And let's see what's still missing. So A intersect B is taken off. What else? A intersects C, and B intersects C. Okay. Now we've taken too much off. Right. This part was taken off right. This part was taken off right. This part was taken off right. But we took that middle part off too many times. How many times did we take it off? We took it off 3 times. We got to put 1. I don't think we need to put 2 back. Because we counted this guy twice, but we took... We need to put it back once. It's a little tricky.
You've counted it 3 times and you've taken it away 3 times, so you have to put it back once because you want to count it once.
That's excellent. Good. Sam just saved me some brain power.
6 times, anything counted 6 times.
Because they're thinking of, I don't know, but I'm going to. They're thinking of this. They're thinking of this being once, that being twice, and they're thinking maybe there's 6 different ways that you overlap here. But there's really only 3.
What did Sam just say?
Doug is asking, why are people making a natural...
The intersection of 3 things that were each counted twice. So you're like 3 times.
Okay, right.
Again.
This formula that I have here for 3 is right. Let's see if we can... You have a question, Andrew?
Well, I was just wondering why we don't turn A and B into one new set, like D and intersect.
You would do that. That's how you prove it. You would, and then you go back to the 2 case. But we're not going to prove it, but you would do that. That's exactly how you prove it.
Can you repeat it?
His question was, why don't we turn B and C into a new set and call it D, and then just use what we did before and see what happens? And he's exactly right, and that's exactly what induction's all about. And if we had n plus 1 sets, we turn n of them into 1 set and use the original formula. But there'd be a lot of notation and unraveling and manipulation to see what actually works. But that's exactly what you do.
But why don't we look at the pattern and simply assume the pattern exists?
There's a nice way to do it. What happens if we're going to add more sets? It's hard to actually write this theorem out. So I'm going to have to describe it to you. Let's do it with 4. What do you think happens? You start out with all the single sets added together. You subtract off all the pairs. You add on all the triples, and you subtract off the single. There's 1 quadruple, right, the quadruple. You alternate plus and minus. You start with the single sets. You move on to the double sets. You go on to the triples of the sets, and then the n of the sets. That's the general rule. This is just dying to hint towards counting. How many of these single ones are there? Well, if you have n sets, there are n of these. How many of these are there? N times n minus 1 over 2. It's the number of ways I can pick 2 people from a group. Number of ways I can pick 2 sets from a set of n people. Just like sending you guys out to do the Xeroxing in pairs. So there's going to be about n squared of these pairs. N squared minus n over 2. Doug, you're giving me that look like you're cooking. What are you thinking about?
What are you saying is n minus?
The number of pairs. So in this case, where n equals 3, 3 times 2 divided by 2 equals 3. That's how many sets of pairs there are.
So the sum of A intersection B.
Not the sum, just how many of these terms are there? How many ways can I pick 2 sets from a collection of 3? I can pick AB, I can pick AC, I can pick BC. I'm just talking about how many of these terms there's going to be.
Show us the notation, please.
No, not yet. All right. You write it like this. That's the number of ways you can choose two things from three things.
How do you say it?
3 choose 2. 3 choose 2, you say. This is way ahead. These are called binomial coefficients. This is a week and a half from where we are now. This is just a little preview. But make sure you get this theorem. I want to do a couple applications of this theorem because it seems like, okay, well, so what? There are an amazing amount of difficult problems that you can just manhandle with this theorem. And I'm going to do a couple of very simple ones today. And when we get into the counting week, I'll do much harder ones. Let me give you an example of one that's much harder that I won't do today, but it's a famous one. You all come to class, and you all bring your lunch. Okay? And you all give me, because I told you to.
Because you're not treating.
Because I'm not treating. There's a lot of different ways I could have given the lunches back. We're not talking about how to count that right now. But of all the ways that I could give the lunches back, how many of them result in nobody getting their own lunch back? No, there's lots. Right. There's lots of ways for me to give the lunches back so that nobody gets their particular lunch they handed me. That's called a derangement, because it's a deranged thing. It really is. It's called a derangement. It actually has applications in particular areas in discrete math, and solving it, one really cool way to solve it is with the inclusion-exclusion theorem. All right, so that's a hard problem that uses inclusion-exclusion. Let's do an easy problem. Let's do an easy problem. There's 12 people. 10 are smart. 5 are computer scientists. How many smart computer scientists are there?
Anywhere from 3 to 5.
You don't know. It's a range.
Anywhere from 3 to 5.
Depends on how you define computer science.
You're not people.
12 people total. All right. Let's do a picture. Here are the smart people. Here are the computer scientists. There's 10 smart people. There's 5 computer scientists. There's 12 people all together. So the union of these two together is 12. The number of smart people is 10. The number of computer scientists is 5. This 12 is A union B. A is the number of smart people. B is the number of computer scientists. I have to subtract off the number of people who are both smart and computer scientists. Smart computer scientists. So what's the answer?
Anywhere from 3 to 5.
Why isn't it 3?
Because that 5 can be in
The universe. The universe that we're not
you have the
going around.
non-smart people too.
There's no people that are not.
There could be a ton of computer
The total number of people in this whole universe is 12. That's
You have to draw the
But you have to draw
everybody in.
around.
There could be non-computer science.
there's nothing there.
There's 2 there.
There may be 2, there may be 1, there may be 0.
Oh, but I'm trying to tell you that there's none. I'm trying to imply that there are 12 people total that are just here. There's nobody outside of this. You know that 10 of them are smart, 5 of them are computer scientists. Then this guy has to be 3. All right.
Wait, so it doesn't require stipulation though that there are no, not smart, non-computer scientists or something?
Yes, it requires a stipulation that all the people All the people are either smart or computer scientists in this universe, or both. Right. Right. There are no... Right.
No stupid, nothing.
Yes, 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 right. There's 12 people in my universe. 10 of them are smart. 5 of them are computer scientists. How many of them are both?
No, you still haven't put it in the range. You're saying that there are no people who are...
Oh, you're right. I have to say that there are no people that are dumb, non-computer scientists. You're right. I do.
It's as difficult as possible for a computer scientist to be smart, yet all these things are true.
All right, I missed that.
Very good.
All right, let me give you another problem. It's a little bit less arbitrary here. This is a good one. How many numbers from 1 to 21 are divisible by 3 or 7? And we'll do the same question with 1 to 21,000. One way to do this problem is just to go ahead and check. How many numbers are divisible by 3 or 7 between 1 and 21? 9. Right? Is that true? 3, 6, 9, 12, 15, 18, 21, and 7, 14. Right? So 9 altogether. All right? Kind of easy problem. You don't need inclusion, exclusion for it. But now I bump up the ante. How many numbers between 1 and 21,000 are divisible by 7?
9,000.
Is that true?
9,000.
9,000?
I didn't mean this to be so easy. Is it really just 9,000? I don't want it to be.
21,000 is simply
21,000
that's
divided by
equal
3
to
is
21
7,000.
1,000 times. And if there are going to be 9 in the first
Oh,
one,
it is
there's
too
gonna be
easy.
9 in the second one, and 9 in the third one.
Yeah.
9,000.
I led you to a way to do it that doesn't require the technique that I wanted. I'll do it my way anyway? All right. I want to do it my way where you really feel you need my way. So here's the way. You'll all forget?
7,000 plus 3,000 minus 1,000.
We're going to do my way anyway. How many numbers?
Woe betide us if you don't use your way on the 6.
Oh no. Are divisible by, here, we'll do 3 or 5 or 7, and between 1 and, say, 1,000. Now we're cooking. I want just to give you an example where inclusion, exclusion is a natural thing to try to do. One way to do this is to enumerate all the numbers from 1 to 1,000 and try. Another way to do it is the way we just tried. Try to find a smaller interval and then expand out. That's a clever way. Let's do it by a brute force inclusion, exclusion way and see how that works. Here are the numbers divisible by 3. Here are the numbers divisible by 5. And here are the numbers divisible by 7. Okay? If you want to have how many numbers divisible by 3 or 5 or 7, that's the case of the 3-set inclusion-exclusion theorem. Take all the numbers that are divisible by 3, add the numbers divisible by 5, add the numbers divisible by 7, subtract the numbers divisible by 3 and 5, subtract the numbers divisible by 3 and 7, subtract the numbers divisible by 5 and 7, add the numbers divisible by 3, 5, and 7. All right. Well, what good is this? This is a classic example of counting the opposite if you can't count what you want. We can't count easily 3 or 5 or 7, but 3 and 5 and 7, and 3 and 5, the ands are always easier to count than ors. Ands are easier to count than ors. Let's see why. We'll get to these ands or intersections in a second, and you'll see why they're easier to count. But let's go through this and get numbers here. A is 3, B is 5, C is 7. How many numbers are divisible by 3 between 1 and 1,000? You just divide 1,000 into 3 parts. That's a division problem. So 333. Number divisible by 5, 200. Number divisible by 7. That part's easy. Now, how many numbers are divisible by both A, B? That means both 3 and 5. If you're divisible by 3 and you're divisible by 5, then you're divisible by 15. If and only if. So all you got to do is divide by 15. Ands are easier to count than ors, almost always. So one of the things that the inclusion-exclusion theorem is showing you is when you have to do things by ors, look for a way of dividing it into pieces that are all made up out of ands. And that's just what the theorem does. So, what's 1,000 divided by 15?
66.
Thank you. And now we have to divide by... Oh, there's a C there. Now we have to divide by 21.
47.
And we have to subtract off another...
35 is 28.
1,000 divided by 35 is...
28.
And we got to add on... How many numbers are divisible by all 3? That means by... 1,000 over 105, there's 9. If you add all these up, did you do it? You must have done it. 533, 633, 670, 675, 60, 9, 7, 643. 543? Math by democracy. What's the answer? Is it 543? Let's make sure we get it right. 543 for the record.
I just did it in my head.
Is it 534? Rob?
I think so, yes.
We have to have at least, we have to have a quorum of 3 who agree.
I have a quorum of a calculator. It's got to be in an odd number. 684. It's 543.
It definitely ends in 3. I just added up the units digit, so I know it ends in 3.
Modulus 10.
Modulus 10, right. 543 it is. The inclusion-exclusion theorem can be used for all sorts of complicated things like that derangement problem I showed you. But you should know what it is, and you should be willing. This is a completely, as an example, more examples of test questions. This question, a simpler version of this question, is a question that is perfectly fine for a time test. A question of truth tables and showing equivalences between them is fine for exams. If you can do the problem set 1 and you've got the basic idea on all these kind of questions, you're just gonna shrug your shoulder and say, okay, why was I so anxious? Okay? If you're not sure about problem set 1, then you've got a lot of work to do. And from my senses, most of you really aren't quite sure yet, and need some work, right? Yes.
It looks like a bunch of the beginning of problem set 2 is this stuff.
Yes.
So the beginning of problem set 2 is also covered by this.
Yes, yes. I mentioned that before. You should definitely look at problem set 2 in order to help you prepare.
So we can talk about those on Sunday.
Absolutely. Sure. Absolutely.
Because there won't be solutions.
Yay! What? No, of course. Right. I mean, look, these problem sets are due every 2-3 days, right? But if the idea is for you guys to learn, if there's somebody who needs me to actually go through every single solution to every problem until you finally discover it up until more or less the end, then we're going to do that. I mean, most of the time that's not necessary, but